pleasure to introduce Professor Harrison Kim. He is the Donald Bigger Willett Faculty Scholar at the University of Illinois in Urbana-Champaign. He is an associate professor at the Department of Industrial and Enterprise Systems Engineering. He obtained his PhD in 2001 from the University of Michigan under the direction of Professor Panos Papalambros, who is a very well-known researcher in the field of engineering design. And actually, Professor Kim is one of the co-authors of the analytical target cascading method, which is one of the well-established methods today for product family design, and I believe he may be saying something about that today. He also held a postdoc position at Northwestern University with Professor Wei Chen, and as well as holding some other industry positions before joining the University of Illinois in 2005. And actually, I had the pleasure of meeting Professor Kim back in Champaign as I was working at Caterpillar Champaign Simulation Center, and so we had the opportunity to collaborate and actually use analytical target cascading for some engine identification problems. So today, Professor Kim is going to be talking to us about complex systems analytics. And with that, please help me welcome Professor Harrison Kim.
Thank you very much. Thank you. Thank you, Professor Norato, and thank you, Professor Elias. These two are very well-respected colleagues in the community, and it's an honor and privilege to be on this campus. And some of those who had the chance to meet with me appreciate it for the time and the help. So the topic that I'm going to talk about today, and before doing that, actually, I understand that there will be some online students coming in, or students or those who are interested in watching live. So this is great. This is fantastic. So the topic is complex systems analytics, a promising enabler for sustainable design and manufacturing. So with that, I'm going to kind of move around a little bit so you can see the screen, okay? So let's start. So I'm going to start with some of the overview of how the talk is going to go, and then we're going to go into some of the in-depth details of this systems design analytics and see how we can kind of wrap this around together. So let's just start. I'm going to show you three very distinctively different topics and see how those three guys are all somehow correlate together. I'm going to start with the food. Okay? So it's the season right now. I bet all of you, including professors, used some of this within the last 24 hours. Okay? Facebook. You might have ordered something from Amazon. You might have watched something from YouTube, right? So let's call that as user-generated content. Okay. Third one is the product lifecycle. So these are basically, you see the consumer electronics and then heavy-duty construction equipment. So let's talk about the lifecycle. So I'm going to show in the talk today how these three distinctively different pieces somehow can be connected together under the idea of predictive system analytics, or I'm going to call it design analytics. Okay? So with that, so before going into the details of this, I'm going to talk about a few of the scenario, a few of the cases. Let's do the first case. So let's envision the manufacturers of any products can predict when the product that they manufacture will reach its end of life and the condition by the time it reaches end of life. Based on the product attributes and then demographics of the consumer who purchased the product, at the very moment they purchase those products. Not the end, but at the beginning of the life cycle. Right? If you call it as a UCE life cycle stage. These are the favorite cartoon characters. You will recognize them maybe. This is a Candice from the cartoon Phineas and Ferb, my kid's favorite cartoon. So he's talking on the phone, and then oftentimes, we have this perception that, well, is it better to keep the product as long as it lasts? Right? You're frugal, try to save money, so let's keep it as long as you can. This is a picture that I got from my backyard, so kind of familiar setting for you guys as well. Heavy snow in the Midwest as well as New England here, right? So this is a few weeks ago. And then this was actually the picture I took from my backyard. This is from the harvesting season 3 months ago in the fall, in October, right? So as you see here, there's a truck coming out, and there's a harvester, and then there's something waiting in the side of the field, and they just go back and forth, right? So you're a farmer, and the farmer might say that, oh, I'm a green farmer, right? So for us, I like to keep my harvester as long as I can, because I'm green. I want to keep things as long as I can, right? Save material, save the product. So that's the oftentimes the perception that people have about the product and the condition and life cycle and so forth. Now let's look at this. So even at the early stage of a product design, the manufacturer of the product can predict which component will be reused, recycled, or remanufactured, or replaced with some of the new components. And as a result of that, you can actually modularize your product design. This is where the product family idea comes in. So you have different products, but if you actually open the product, there are multiple modules. This is the ARA, the cell phone project. You can actually purchase these different modules. You can assemble your own phone, right? So your phone might be different from somebody else's phone. And then you may upgrade it. If something breaks down, you can just replace those parts, right? So the modular design under the idea of product family is very much possible. And this idea of the modular design is now becoming more prevalent across different spectrum of industry as well. I took my students one time to this cell phone company, or cell phone remanufacturing company called Recellular back in Michigan. So as you see here, a lot of companies, they obviously manufacture new products, but also they are now into remanufacturing as well. So Professor Norato, he worked for Caterpillar. Caterpillar had a reman in Mississippi. John Deere has a reman in Springfield, Missouri. So what they do is, actually they take out the engine from the used machine, remanufacture it. Basically, they do machining, replace some parts again, sell those engine as a reman engine with the same warranty as if it's a new engine with a discount. So from the consumer's perspective, this is actually a great deal. I'm getting Caterpillar engine or John Deere product with the same level of warranty but with a deep discount. And they guarantee that this is going to work as good as brand new, right? And we see a lot of things from this consumer electronics world as well, like companies like Gazelle. So the way it works is that average cell phone life is about 18 months. So if you're a college student, you may keep your cell phone for 10 months. You drop something, and they break, and you got to redo one. If there's someone like me, I tend to keep a little bit longer, right? So average is about 18 months. Now, if the product reaches its end of use, and here comes the iPhone 7 comes out, and you're using iPhone 6, you want to actually upgrade your phone. So you can actually go to this website, gazelle.com, type in the cell phone spec that you have. I have iPhone 6, and this is the memory size, and they give you the price that, oh, your phone is worth $250. If you agree, they send you the box. You put your cell phone in the box and send it back to them. They check the condition. If it matches, they send you the money, $250. If you do that right before the release of the brand new product, probably there's a good chance that you can have a higher value. But if there comes a new product comes out, and your one generation older product, the value diminishes quite a bit, right? So that's the kind of scenario we're looking at. So manufacturers, not only they look at new product manufacturing, they tend to now spend more attention to reman market as well. It's growing and emerging, right? So with this idea, I'm going to give a quick overview of where my research has been going. So Professor Norato mentioned that the target cascading. So when you have a complex systems that is composed of multiple systems and subsystem components, how do you design that? How do you optimize that? So I developed a method for the target cascading, ATC, which has been used quite a bit, and there's been follow-up study by several students in different places. And then after joining the Illinois, I started doing some of this analytics type of work. We call this trend mining design, and embedded into life cycle aspects of the product design. About 1/3 of my research portfolio is about the energy, the renewable side of energy. So I look at this hybrid of renewable energy generation. So the configuration is that you have a solar, wind, battery, and a generator. How do you integrate, how do you optimize system under the exterior weather-related resource, right? And then how do you optimize the layout of wind farm under this different resource availability and so forth, right? So design under a certain type of theme. And I have some collaboration with the operations research colleagues who are into the distribution of the electricity, while I'm into the more of the generation of the renewable energy. So I'm not going to talk about all these things today, but I will talk about particularly these two in the context of the analytics, in the context of the system design, and how you can actually embed it in the context of the system and the product lifecycle. Okay? So with that, let's go into a little bit detail. So let's start with this. How does the CDC detect influenza? So if an individual shows influenza-like illness, we call it ILI, you go to see a physician. Physicians, they compile this data and they report to CDC on a weekly basis. I got this map from the CDC website, and it changes every week. Right? This whole process, as the color changes right now, it takes about 1 week for this from the symptom to the compilation of the data and shows in the map. You are a healthy person, I'm a healthy person. If my flu prevention solely depends on this map right here, right, you might have gotten your flu virus a week ago, which is already too late. Right? And by the time that you know that the flu is prevalent in your area, either you are already sick or you already recovered. So this 1 week delay was quite of a significance. Now, with this, how does Google do? So if an individual shows flu-like symptoms, the person might actually go to google.com and type in the keyword like flu remedy or flu symptom, right? So Google actually had a website called google.org, flu trend. They can actually compile the individual search query data for the time and location when an individual sends the search query. This is the chart. The red line represents the CDC data you saw. The black line represents the Google compilation. Right? They match pretty much identically. By the way, this thing happens pretty much all around the world real time. So if the 1 week delay was a significance, if you look at the Google this one, this is obviously pretty much real time. So I had a conversation with my friend that at that time was working at Google. How can we use something like this for system design? And that's the idea of this trend mining design and analytics side of the thing. So with that, let's go on. When I look at something like this, so in your home, in your drawer somewhere, you have probably an old cell phone sitting somewhere there. And when you go to this, all these old TVs, there's so much of them, right? So, for example, year 2009, in the US, there are about 140 million cell phones retired. Less than 10% of them went through some sort of recovery cycle. So, from my engineering perspective, this is a problem. There's a lot of materials, precious metals. These are all not going through meaningful recovery channel. We are just dumping them in the junkyard, or we are burning them in the incinerator. Right? So, is this a really waste, or is this something that's the opportunity we can tackle as an engineer? the underlying theme I want to kind of embed in the talk is that the product or system lives a life. So when you design and manufacture a product like this, comes from the design and manufacturing. Manufacturing involves, before that, you have the material extraction. And then, once the product is sold, it goes into the hands of the customers. Customers, they keep the product for whatever the life cycle that they are basically going to use. And then, you provide regular maintenance. After that, it goes through this end-of-life reverse logistics cycle. Right? So this is the kind of the overview of the entire life cycle. Now, when you look at environmental impact, for example, most of the environmental impact for this particular machine actually comes from the usage phase. So the usage phase, in terms of the fuel, in terms of the emission, counts for about 75% of the total environmental impact. So when I look at metrics like environmental impact, if I ignore this usage aspect, I'm missing big chunk. So this idea that capturing users' behavior and link that with this metric that you're evaluating, for example, environmental impact, the usage portion is going to be a big chunk. Here's another snapshot. For this 824 loader, John Deere products, this is equivalent to about 12,000 iPhone, 10 sedan, and half of this tractor trailer in terms of the normalized environmental impact. So this is a big deal. If you don't do a good job in estimating the environmental impact in the context of entire life, here, climate change and so forth. Now, the problem was that I talked about 18 months for the cell phone life cycle, right? If you look at this laptop, for example, people use it for about 4 years. Wash and dry for 14 years. Machine like this loader, it's about 20 years. And then, if you look at the distribution of the age of this major component, the parts, this all comes with different variability. So the problem was that, remember the 1 week delay was quite of a significance? You're talking about years and years of the time that you have to model to predict in a meaningful and accurate way to assess something like the environmental impact. Right? Because of the nature of this variability. So this turns out to be actually a very, very difficult problem. One more is that, okay, I talked about the iPhone 6 right before the release of iPhone 7, the residual value. Depending upon when you declare the end of use of a particular product, it is actually time-dependent, time-varying function. The residual value of a product, it diminishes as time goes on. And ultimately, it goes reach the zero value. Right? So how do you actually incorporate some of these characteristics of part and components in the context of calculating the residual value and the environmental impact? That's also a pretty difficult problem to do. We coined the term called the green profit. Basically, one of my former PhD students, Min Jung-hwa, she termed the something called the green profit. So the companies oftentimes, they don't want to do this remanufacturing. Perception that they have is it's expensive. I have to go through recycling, remanufacturing, something new that you have to do. But can we make it such that if you optimize those decisions in an optimal way, the whole activity can be profitable for the company. So they do this not just because of for the sake of their corporate image, but they're actually doing this to make money out of this one. So to do that, again, as the product ages here, there's a different degree of the slope of the diminishing value and associated this remanufacturing concern coming out of it. So the key idea that I want to embed here was that whatever you do in the context of life cycle design, the time aspects, the generation aspect should be one of the key considerations that you have to have, which is inherently very much hard. If a single stage design is difficult, this is going to be even more complex aspects of it. So with that idea, let's look at what happens in the reman. When you go through the remanufacturing process, this is what happens. When somebody returns a product, they are disassembled. And then this is a picture I think we got from a company called Silverlight in Michigan. So I took my grad students to this company. that manufactures or remanufacture cell phones, they actually take out the phones and then wipe out all the data. And if the phone is recoverable, they sometimes replace the battery and then reassemble it back and sell their products in eBay or Amazon. If the phone is in such a poor condition, it's not recoverable, what they do is they just shred it and then just melt everything, right? So there are different degree of recovery operations. We call this as a remanufacturing versus recycling. When you say recycling, you melt and then recover material. If you go for the reman here, this is actually better in terms of retaining the residual value. And then if you cannot do anything, basically toss it. Right? So with that, basically, the incoming material, you have to have some consideration because you cannot really control. People return their product in different time and different conditions. Right? And then if you look at this as the entire network of reverse logistics, there are many things you have to consider in the context of the balance, input and output. So with that, let's look at this a little bit more carefully. So the bottom line that I wanted to take in this slide was that, well, you want to maximize the profit from a line of new and reman products. So the company, they're considering going into the reman business while keeping their new product manufacturing business as well. And then they're subject to some of this minimum environmental impact savings. Especially in Europe, there's a strict requirement that a certain percentage of the material or impact must be saved, must be returned as a credit. Otherwise, you have to pay for the penalty, right? So these are constraints that's actually a realistic constraint that's coming out in industry and the market. So how can this be all integrated? So I'm going to talk about some of this analytics side and the life cycle design and see how they can be all kind of integrated together with this. So let's go to this user-generated content. So if you go to places like CNET.com or Amazon.com or eBay, you write reviews. When you purchase a product, you actually look at the reviews, right? So I created an account in CNET.com and then went through their reviews. Their reviews are actually quite interesting, that people write the pros and cons and then write the star rating, right? And then they talk about these different things. Now, not only people write the reviews, this is actually something called JD Link, Product Link, and CareTrack. Product Link is from Caterpillar. JD Link is from John Deere. And CareTrack, I think, is from Volvo. What happens is that, you remember this General Motors car that had this GM OnStar? So each car has this transmitter. So under the telematic system, now you sign the contract, and then every half an hour, all the machine, they send the entire machine diagnosis data to the data center. So I actually took a look at some of this data. Very noisy, but at the same time, it shows the condition of the machine. Is it idling? Is it going through some sort of a mid, low, high loading condition? Whatever, right? And then the data center collects for every machine in North America, for example, every half an hour, the machine data is collected. So look at the review data people typing in. Look at this machine diagnosis data. Now, data is there, right? What do we do with this? When you look at this, particularly the customer review data, I'm going to go into a little bit of detail. So when you look at the customer reviews, for example here, this is the snapshot of this CNET review. You write pros and cons. And for each of the products, you just look at this. This particular attributes or particular feature of the product shows up in the pros section. This feature shows up in the cons section. Then you can probably guess that if people talk a lot about particular feature in the pros section, this must be something that people like. If people talk about cons section, that means that something actually hate. People hate those features. There's no 100% match, but it's pretty strong correlation between those two. So if I show this to like freshmen to University of Illinois, University of Connecticut, they might think that, okay, why don't I just run open source dictionary and then count all the words that are feature related, and then tag them for each of the time period, and see what happens. And if you have more of the pros, that's probably better. less of the con, that's better, or vice versa, right? The problem was that if you actually run the dictionary, the word like a Siri, this is not shown in the dictionary. These are new words that came out. So you have to have actually a better way to detect. We call this a part of speech tagging. So there are certain words that are associated with the features, and you can actually divide those into pros and cons section. If somebody writes a review like this, for example, let's look at this. Included memory is stingy. You can divide the sentence into verb, noun, verb, and adjective. Usually, feature-related words are associated with nouns. And you remember the review was divided into pros and cons section. You trace those with the time when the review was written for the particular product. And then if you tally all those them together, you can probably plot those under the time horizon sequence. So keep the life cycle thinking in mind. Okay, the product is released, people are using it, and then you are just collecting this review data, or you are collecting the JD-Link machine diagnosed data as time goes on. We plot, if you have this kind of data, for example, let's say you are in the time horizon is dotted line, and you collected enough data, let's say in the past, for 16 months, 12 months, 18 months, whatever, right? What happens is, if there are some features in the red line that's emerging, you can probably assume that it's going to continue to go up. Some of the data might be static. Some of the data might be go up and going down. So actually, there's a well-known decomposition method in the time series domain. You can decompose the data into level, trend, and seasonality. Methods such as port printers, and there are many other methods available out there now. They're dividing the data, and if you have reasonable confidence in your past data, for the immediate near future, you can probably see how it's going to be plotted with the dotted line. Okay? With this idea, we started this test website, trendmining.net and .com as well. So we went to cnet.com, and we swept the entire review data of cell phones in the US for several years now. And then now we have the data from eBay and Amazon. Unlike the cnet.com, eBay and Amazon is quite interesting. People don't divide the reviews as pros and cons. So it's just a single paragraph. So you have to have some sort of sentiment analysis to see whether it's a good or bad reviews, right? So the idea is that basically you collect for a particular product category, as time goes on, tally and count them. And then we collect the total of, for example, for the Apple iPhone model, and then you collect some of this trend coming out and some of the top features coming out of here. And then, as of a few months ago, under the cell phone category, there are a total of 1,600 products. We have a total of 55,000 reviews. And we have some new data coming from different sources. But the bottom line is that I want to collect this data in a meaningful way to detect the pro and con features of the product, and I want to see how they're going to behave or how the market will appreciate or de-appreciate those in the near future. This one has implication for something like this telematics system you saw in the JD-Link or CareTrack or whatever the system you have. If you know that you have collected enough data and that it's coming from the reliable source or the single machine that you are tracking.
Yeah, the reliable is the problem that I have.
So,
okay, especially on the previous review stuff.
Yeah.
What if you have got people that are just putting in good reviews?
Yeah, so right now, if you look at run the sentiment analysis, the accuracy is about 65 to 70% match. Mm-hmm. So the reason that we like the CNET review better was that it was divided pros and cons already. And then, but eBay and Amazon, they don't divide the review. So you have to run as if it's a neutral text and then run the sentiment analysis. So far, the result is about 70%. So people write maybe 10 words, 7 words with a positive sentiment out of 10.
No, well, I'm just saying that if you have somebody that is already your own people writing your reviews.
Oh, you're hiring some people to write your. Yeah. That could very well happen. But my guess.
Like in stock exchange, they do.
Yeah. So, but my take is that if you collect enough number of data, so I have a
Hopefully
55,000 review, so there may be a fraction of the data that you are hired by to write good or bad reviews, right? I'm sure it's going to happen a lot in the election cycle.
Absolutely.
So, and then you can actually cross-validate those. You divide the data into 10 different groups, and then cross-validate each other, right? Very good point. So the idea is that if I had that kind of tracking capability, I want to use that to predict the near future of the system behavior, right? So with that idea, what happened was this one. So go back to the idea of the environment impact assessment. And if I had, let's say, amount of the diesel fuel that is being used, and it comes with this cyclical behavior, for example. So far, if you want to use the average method, taking the average of this red line, right? Of course, it's not going to be accurate estimation. And if you have to provide some sort of maintenance or fix in these valleys or the top or whatever, if you take the single average, it's not going to be obviously a good indicator, right, of the system behavior. So going back to the idea of that, okay, here I have the past data that's collected, and then as the machine goes through wear and tear, you get to spend more and more and fewer, right? It goes through wear cycle, and then I want to predict at least the dotted line or the real values by some of this method. So what we did was, we looked at the particular example of harvester. Interesting thing was, people look at this harvester, there's a harvesting season, right? You use a harvester for 2-3 months of a year, and then it goes in the storage space. So if you use the traditional time series analysis for decomposing the data, this flat line, they very much affected the accuracy of the prediction. So we had to have a way to chop off this flat line, and then go back to the previously available, like in the predictive method that's out there. So there are some techniques available for them in terms of how to segmenting the data and so forth. And we just finished the one paper and published it in the journal. The bottom line idea is this. If you have a system that shows this extended time period idle, you eliminate those, predict, and then put those back up again. Right? So that's the idea in a nutshell. And for that, we embedded a couple of different techniques. In the time series domain, exponential smoothing and ARIMA, these are basically ways to decompose data in a nutshell, level, trend, and seasonality. And then you have different components, so you have 3x5 combinations. And you can actually plug this in, try to fit as a model, some optimization technique behind it, and then here comes some of the predictive capability. So the bottom line idea is this. The reason that we were able to publish this kind of work was that for the particular system that we're looking at, the complex system, and there's unique aspects of data that require some of the segmentation and predictive capability, and here comes some of this validation job that we have. So switching gear a little bit, so go back to the remanufacturing idea, the idea that you have this green, right? Companies oftentimes, they are hesitant to go into the green business, remanufacturing business, because there are issues, pricing, production planning, environment assessment. These are all integrated pieces that are affecting, if you look at the system design and optimization problem. Very complicated pieces. So we have to look at some of these aspects of this. Now, the objective is two. You want to maximize the profit for companies. You want to maximize environmental impact savings. Let me repeat that. Without profit, you're losing money. Companies, they don't want to do it. Right? Total environmental impact savings. Without that, you might violate the regulations. So these two go hand in hand. From the optimization perspective, this is a typical multi-objective or bi-objective optimization problem, where you have to come up with the pricing, quantity, and a lot of logistics issues embedded in the system design problem. So how did we do this? If you look at this, so think about this as an ABC, as a full product, right? When you get those end-of-use ABC product, you have to disassemble those. So ABC is disassembled into AB and then C. AB is further down to A and the B. So when you go through this assembly operation, there's something called the transition matrix here. +1, -1 indicate disassembly and reassembly back. In that process, not all the end-of-use products are reusable. So something like this, 60% and 40%. You can recover 60%, 40% you have to replace it. Right? So that's kind of the overall nutshell how the modular design can be disassembled and put back for the remanufactured product. Now, if you look at this, 3 pieces of components for ABC product, this is a full transition matrix that you described. Think about John Deere product. Think about United Technology product. You're talking about huge sparse matrix that has to define all this assembly sequence. Right? With that, the idea is that you take something, do some operation through this transition matrix, and you generate the remanufactured product. You're not sure that's what's happening. With that idea, what do? You want to look at the profit aspects. You look at the profit from the new and reman. By the way, the company is doing the new production, and they do reman operation as well, right? And then with this idea, there's some cost involved, recycling, take back, production, share part, and so forth. And there are some of the constraints associated with the take back availability, production quantity, upper limit for the reman, and then environmental impact savings. So these are all the details I'd be happy to share down the road. But the bottom line is that you take something, you do something in manufacturing operation, reman operation, while you are keeping your new product intact, and then there are environmental impact aspects and also logistics aspects that are embedded in this problem. And then some other constraint part of this process. So we looked at this case with the cell phone. So when you look at this iPhone, right, this is overall product architecture hierarchy, and some parts are shared product family. So 16 gig, 32 gig, they might share the same battery, right? But the memory chip is a different size. So if you look at this overall architecture, some part will be shared part, some part will be unique to particular product variant. And with that idea, for this particular product, we look at some of this reman case. I'm going to go into deep dive into this particular water pump case by John Deere. So let's say in a hypothetical scenario, the company manufactures new pump only. And there's a third-party OEM that manufactures reman water pump. So from the Deere's perspective, again, this is a hypothetical scenario, this third-party OEM is taking over their market share quite a bit. Look at this as a 55%. The reason is, it's cheaper. The brand new is $100, reman is $50, and then obviously new and reman is different, but the price is discounted enough, people are actually buying those. So companies are deciding, okay, here's a market size. We want to contemplate whether it's worth going into reman market, in addition to the new product manufacturing that we are doing right now, right? So we look at some of the scenarios. We have to construct some utility. So market size is the 3,000, and customers prefer, obviously, Deere original product over low-priced OEM. People prefer the Deere product, but it's expensive. So you got to embed some of this consideration in terms of this condition, brand, and price in constructing the overall utility. And you're optimizing your overall condition, whether you do this new and reman, and then decide what the perceived utility and so forth. So there are a bunch of utility that can be embedded behind this as a result. But here's the scenario that we looked at. Remember the objective function, we looked at 2 objective functions. Maximize profit, maximize the environmental impact savings under some of this constraint. In the optimization world, you can actually embed this as an epsilon constraint approach. You use second objective as a constraint and put the epsilon and try to relax those epsilon. Construct a parallel frontier, right? So what you do, the result is this. This is your baseline. If the company doesn't do any reman, they do only new production. This is the baseline that they're doing right now. They decide to change their pricing a little bit. As a result of that, they were able to sell a little bit more. right? If you lower down your price slightly to $89, as a result of that, market share goes up, right? And then, as a result of that, your profit might increase slightly higher as well. So this is, if you stay with the new production only, this is as best as you can get. But the problem was, look at the x-axis. There's no impact savings. Government tells you now that you got to actually save environmental impact. Okay? So what happened was, okay, for the first scenario that we looked at, they somehow decided to abandon the new production and then go for the reman full 100%. What happened was, depending upon their overall pricing and all the things going on, this blue line represents the corresponding profit that comes out of the reman operation only. So as you see here, if they do a lot more of the reman operation, environmental impact savings is huge, but you may not actually make much money out of this one. And you can control these different epsilon values, and this is the trajectory that you're going to look at it. Now, from my perspective, the model that we developed was that, okay, why don't we allow new and reman together, okay? And then control the amount of effort in an optimal way under those two objective functions that you looked at. And the part of the frontier that comes out is this red line. So what happened was, remember this solid line was your baseline. That's your profit in the beginning. And then this red, the black box here, dot here, is the maximum they can get as a profit. By doing this reman and the new together, under this optimization problem that you saw, you can actually generate these red lines above the baseline profit that you have. So what happens? You look at this, x-axis is the positive environmental impact savings, and by the way, you make more money out of this one. So we coined the term called the green profit out of this one, in this case, right? So the perception, if the perception was that, well, you cannot be green because we're going to lose money, guess what? You can be green, and you can actually make money out of this whole operation as well. Right? So this could be actually very powerful.
That depends on the utility function that you came up with.
Of course, yes.
Which depends upon the human nature.
Yes. So to fit the utility model, we use this those three aspects: brand, price, and what was the other one? But anyway, there are different ways to construct the utility function. Right? So this line might go up and down a little bit, but the idea was that under the current linear utility function that we had, we are able to identify that there is some region that you can actually make a profit out of this one. Right? So, last part of the presentation. So when you look at this reman product, right, the perception of people have that reman must be cheaper, should be cheaper, otherwise nobody will buy it. Right? So go back to this time varying scenario that we looked at. From the manufacturer perspective, how do you set the price of the reman product? Okay? So you have to look at obviously the residual value of the product. How do we do this? This is where a lot of engineering design expertise can come in. What I'm saying by that is that, look at this PC example. There are different types of parts available. So let me go through this. If it's chips, the chip technology changes very dramatically, right? And also, at the same time, it's very much robust, very low failure rate. On the other hand, if you look at the optical drive, the technology is the same, right? At the same time, it has very high failure rate for the DVD drive that you have. Something like this chassis, it's very cheap. There's not much significance of the sophistication embedded in there, but at the same time, there's a minimum failure rate. So depending upon the part characteristics or design characteristics, you can actually look at these different categories. If I know this, I'm going to define something called the generational difference. So when people look at the value, the residual value of the product, was it 2 generations ago, 3 generations ago? As the generation goes on, you're going to see the diminishing value of the residual value, right? So you got to define something like a generational difference. And then the proposition that we tested here was that there must be some cost saving when you do reman operation. There is a function of this cost, which is you look at the generational difference and associated with the penalty function. And then you look at this cost savings for reusing the part. Let me just go back to this one again. This one, there's a probability that a part is reusable, both physically and technologically, can be modeled as something like this. In other words, depending upon the generation of the product, some of the product might be too old that it's prone to failure, but also multiple generations ago doesn't bring much of the residual value. So those aspects should be captured with something like this F function. And then, depending upon the volume of the things that you handle, there is associated cost. Associated environmental impact, also you can model something of this nature. The proposition that we had was that, okay, let the company do this Reman operation. If you were to calculate the net profit, which is price minus cost, multiply the total production volume that is associated with the function that you just saw in first two propositions, this is the overall net profit function that you can construct. Now, the corollary that we had was that if you call this beta as the price, the 70%, 60% of the price of the new price, right? So if you do Reman engine, it should be cheaper, right? So that ratio beta, fraction of the new product price, will change as time goes on. So there must be the beta range that ensures the profitability, which it says here is this. Reman is more profitable only if consumers are willing to pay more than beta star of a new price. You want to sell this Reman product, but if the customers don't buy the price that you set, you're in trouble. So you want to identify the beta star or above. So for example, if the product is 4 generations ago, the Reman makes sense only if customers are willing to pay 81% of the price. If consumers are now willing to pay 81%, don't do it. But if they're willing to pay 90%, right, go for it. Second, if you were to set the price to 70%, you know that you gotta set 70%. Up to what generation do you have to go to recover the product? This shows that about 2.5 generation or newer product. If it's a 3rd generations ago, don't even bother to go back to recover any of the part. So the idea here was that we understand the Reman should be cheaper, but how to set the price, or if there comes some constraints by the regulators and so forth, how do you find the optimal? And we're able to show some of the simple profile of this one. Right? So wrapping up this talk. So where does this research go to? So you saw some of this life cycle aspect, some of the analytics aspect, and integrate together in terms of product design, and you get some of this ear products and so forth. So when we did this, it was interesting. Chicago Tribune and USA Today picked up for the study that we did for the cell phone case. So there's a consider cell phones fake when designing them. When you design something, you gotta have the end of life in mind. So that's a kind of fun recognition. And then obviously we had a project with the Caterpillar, John Deere, and then some of this NSF funding that are part of this thing. More than anything else, this is one screenshot that I had in front of the building that I had. Some of my former students. I'm the happiest guy. It's all about fun. So this is the first guy, second guy, third and fourth PhDs in the lab. And 3 of them went to academia, 1 went to industry. And this is one of those backyard party that we had. Over the Christmas, one of the students sent me a Christmas card. I still remember the salmon that you cooked at backyard barbecue. so having fun, enjoying things, and some of these recognitions comes along. So wrapping up, you look at the analytics aspect, you look at some of these life cycle aspects, and then I kind of packaged it together in the context of predictive design analytics. And you saw some of the examples of the consumer electronics and the John Deere products and so forth. So there are many opportunities you can tackle this out of this, and for which being green, my party message is, being green can be sustainable by carefully linking product predictive analytics and design and manufacturing. engineers, we know design and manufacturing. Now the analytics capability is coming in. If we integrate those pieces together very carefully, I think we can make this as a successful story. Well-designed products enable more profitable, sustainable end-of-life product take-back and recovery. You can close the loop by developing those quantitative tools, and then analytics capability integrates the product design, manufacturing, and sustainability. So what's new? So one of the new things I'm doing right now, going back to the CNET data, we're very much interested in finding out the market share of a particular product. Nobody publishes those. So as a pseudo measure of market share, we wanted to track the ranking of particular product sales. So if you go to Amazon, type in this particular product, it shows their sales rank. And we traced it for the last 6 months. It changes day-to-day basis, right? So if you don't have the market share, the idea is we're going to design a product that is taking more market share. So how do you capture attributes in a predictive manner when you design next generation of product that's going to lead to a higher market share? That's the kind of idea. And then we look at some of this complex system comparison and so forth. So the bottom line is that here's the overall life cycle and different aspects of the impact areas, and that basically wraps up my presentation. Thank you very much.
We have time for a couple of questions.
Yeah. What is the beta star that actually people use? For me, that beta star has to be a lot lower. Even if it is 0, I may not want to buy it. Okay? So, have people done any work on how human specific?
Yeah.
Like, what is the...
So that's where the utility model comes in, right? So what we looked at here was that we provide the scenario, the value. So if you want to go for up to third generations of O, you can set the beta maximum like this. If you want to set the beta as a minimum of 7%, you can go back to up to 2 generations of O. So those are the things that we want to convey. Not necessarily for the particular product you have to set this way, because it depends on the utility function you use.
Right.
But here's a...
So what are the typical humans would remanufacture? By remanufacturing, which is new, right?
So if you go to gazelle.com, you can actually buy remanufactured iPhone, right? So if the iPhone 6S is like now $1,000, you can get it for, I don't know, 600, 700, something like that, actually 500, right? So if they have used some of this demand modeling scheme that's behind this, the pricing must be reflecting some of this willingness of the price that customer.
Okay. Has anybody considered if there's already a remanufacturer present in basically competitors to a company, an OEM, trying to remanufacture? I know I'm wording this really badly, but has anybody considered competition between the OEM versus a remanufacturer and how that affects the price point?
Oh yeah, the example that we showed in the water pump case,
Yeah.
there's 2 agents in the market. There's the competition aspect. So you have you and we have a third-party reman. Right? The way that the market share is set is basically it's a Nash equilibrium problem. So what we did was we allowed reman under the first agent together. So the company 1 does new and reman together. And then company 2 does reman only. And obviously the market equilibrium point will be shifted. That's how we show it. So that is definitely pricing that was set by the market equilibrium of the game theory.
We have one last question. About you had a question?
Yeah, and we can do it later also. So we talked about the utility function and we talked about the remanufacturability. But what about safety? I mean, these consumer products are okay, in terms of you can reassemble, remanufacture. But when it comes to safety critical aerospace products, for example, how do you factor in safety? Because you can't use this life limited part if you're reassembling something.
Yeah, I agree. So if you look at the transition matrix, not every part goes through evaluation of the remanufacturability. Certain parts, due to safety regulations and so forth, you must use new parts all the time, right? But some of the parts, it's okay to go through reman process. So the idea of using something like a transition matrix is to differentiate that if there's some part that you must use brand new, even if it's a reman product, right? That can be reflected in the operations we have developed.
Right, let's thank our speaker again. I should say that the student that went to industry was